Today is a very special class in CS109 because this is the first class where we're actually going to be talking about probability. It's about time we're a class on probability for computer scientists. So get excited. We will get deep into what probability actually means today. Before we jump into anything, though, a couple announcements. This is a fun thing. Hey, I like to tell stories on Fridays. It's just one of the things I do. So I'm going to tell you guys a short story to get our class started. An important announcement, much more important than the Friday announcement, is that section signups are open, and they're going to be open until Sunday at noon. You have between now and Sunday at noon to fill in your section time preferences, at which point we'll close the queue. So you want to make sure you get signed up before then. It's not first come, first serve, but just make sure you hit that deadline. Some of you guys have not seen Python before, or you'd just like a refresher. There will be an online review session at 5 o'clock today on Friday. You can go check it out. It will be recorded, and we will post the recording within a reasonable time. But if you can go live, fantastic. And then finally, we're going to do something today that's never been done before. I promise you something completely unique in the world will happen by the end of lecture. But quickly, story time. You know, there's a lot of stories I can tell, but maybe an interesting one is a lot of people ask me, why did I grow up in Kenya and Malaysia? And of course, the answer is my parents. They brought me to, well, I was born in Kenya, but I lived there because they chose to live there. And so the question really becomes, why did my parents end up living in Kenya and Malaysia? And the story was, my mom had grown up in Europe and my dad had grown up in Philadelphia. And then they met one day, and the story of them meeting is kind of cute. I guess my dad was a high school teacher, and during the summer he went on a trip, and my mom went on a trip in the same direction. They met, fell in love. But they were living in two different cities, Boston and Philadelphia at the time, and they were doing long-distance relationship, and they're like, maybe we should find some place to live together. So on a date, they thought, oh, you know what we should do? It would be funny. We should apply to jobs in different corners of the world just to see what would happen. And so they applied to jobs in Brazil and France and all these different places, and they got a response back from a job in Jordan that was for both of them. And they're like, you guys could go live in the Middle East. My dad never left Philadelphia. And so they're like, okay, let's go. And technically the story went, they had sent a check in the mail. This is in the early 80s. And they cashed the check, spent the money, and then they're like, wait, we can't do this. But they'd already spent the money and they couldn't return the camera that they bought. So they're like, we'll go to Jordan for a year. But they went to Amman for a year. And when they were in Amman, they had an incredible experience. And they met some Kenyan people who said, hey, if you like Amman, you're going to love Nairobi. So you can come and you can teach over there. So they thought they'd only be gone for a year. They didn't sell any of their things. They got married over 2 days' notice and then went on. And they said, we'll call this our honeymoon. And then, when we're done with this, we'll come back to the States. But it never stopped for them. They went to Kenya, and they were there for about 15 years, and then they went to Malaysia, and they were there until earlier last year. And the cutest thing is, if you ask my dad about it, he'd be like, yeah, just the honeymoon never ended, which I think is just very adorable. Also adorable, section signups. How do you do it? You go to section, sign up form, you get a form like this, you have hard questions like what is your name and what is your availability of time. Problem set's out. As you know, problem set 1 has been out since Wednesday. A couple of frequently asked questions is, there's that cool check answer feature. It's fantastic. You can know if you're doing the thing right. I think somebody asked this, and it's just worth repeating. Can you check many times? Absolutely. There's not a penalty for checking many times. Are you just going to grade us on whether or not you get a green check mark? No, you have to give explanations for all of your answers. So even if you check your answer, you get the right number, please explain your work, because it's the process of explaining your work that we really care about. And it is important that you guys learn the way of expressing ideas in this subject, not just getting the right answers. How much explanation should we provide? We talked about this on Wednesday, but certainly looking at worked examples gives you an idea of what it should look like. Do you have to do all your work on the app? No, absolutely. You could do it by hand, take a photo, upload the photo, whatever you want to do to get your answers. Example answer of what sort of explanation we want is check out the Enigma machine. This is a question, and here's the sort of level of detail we'd like to see in an answer. Super small thing, about half the class has started. This is how many questions people have finished. So some people have finished between 0 and 4, some people between 4 and 6, 6 and 8, 8 and 12, and 10 and there's even a small number of people who did the whole problem set. About half the class has already started, and I would encourage, if you haven't already started, to get started as soon as possible. After today's class, you'll be able to do every problem on that first problem set. So if you want to be done by Sunday and then just party the rest of the week too, you absolutely could do that. OK, a Python review session you know is going to be online, and you can find the link on the website. That's all we have for logistics. Any questions before we jump into content? OK. Oh, yeah, question.
Are any of the sections online?
Yes, 2 of the sections are going to be online. It might depend on demand. So for the people who want online sessions, I think we might be setting the time based on that demand. Good question. We don't have to book rooms for online. OK. So in our last great class, we did counting, and not easy counting, like pretty serious counting. And we did 3 particular versions of counting that we're going to build upon today. The 3 types of counting that we did last class is we talked about, let's say you have n items. How could you think about different ways of counting sortings of those items, so orderings of those, where order really matters? And we did a different task, which is like, let's say you have n items. How many ways could you choose a subset of k? And that's a different task because in this case, we don't really care about the ordering of the subset you choose. Just we care about which items were chosen in the subset. And a third task we look into is, let's say you have n items. How many ways could you put them into, say, R buckets? In each of these cases, we often thought about distinct versus indistinct. And what I want to point out, though, is we had a distinct case for each of those. And that's what you really need to know to take counting into probability theory. You want to know how to do sorting for distinct items. You want to feel very comfortable with how you could choose k subset from n distinct items. And you want to do the bucketing with n distinct items. We're going to use them today to the point where I wrote those 3 rules out on the board. And I just, instead of having R buckets, I had k buckets. OK. A little bit of warm-up to get us going back into the mindset of counting. I have this whole narrative of, if you wanted to do something like make a DNA tree, there's lots of calculations like this that require you to do a comparison between every one of n different elements. So in this case, I'm going to give you n animals, and you need to do a calculation for every pair of animals. For this problem, I don't want you to worry about what the calculation is. I want you to count how many calculations there are. So n animals, and I want you to do a calculation for every pair. How many calculations do you have to do? Does that question make sense? And I want you to just think about it. So if you have an idea, if clarification questions, ask them now. If you have an idea, tell it to the person next to you. Clarification questions before we jump in? Yes?
Can you explain the question again?
Yes. OK, so let's say you have n animals. You have all of these different animals. And I want to count how many unique pairs of animals are there. So like, this is a pair of animals, but this is a different pair of animals, and this is a different pair of animals. So how many pairs of animals are there? And there's a story here. If you wanted to make like a DNA tree of all those animals, you'd have to do a DNA comparison between every pair. Good question. Making sense? OK, take a moment, talk about it with the person next to you. Let's see how many different pairs of animals are there. OK. Just a warm-up. I like this problem for a few reasons. One, I've just needed it as a computer scientist. There's been many, many times in my life where I had to do this calculation, and I had to pause to decide how long would my calculation take. And sometimes this sort of work could take you, a couple hours of compute. And so you want to be thoughtful about how many comparisons you have to do. I also like it because there's several different ways of coming up with an answer. Did anyone find a way to solve this problem just by directly inferring one of these rules? Yes, in the back. Yeah.
Well, it's just you're choosing 2 animals out of how many there are.
N. Sure. We don't like to count past 7.
Counting is a bit more difficult.
Yeah.
So you choose 2 out of the n animals, and that's your pair.
Yeah. OK. If you count it this way, so your n choose 2, will you ever end up with animal A with itself? No, it doesn't give you. N choose 2 is always thinking about you have these n things that I'm always going to get 2 distinct items. In n choose 2, if you get this first and then that second, will you get a different outcome which has them reversed? No. OK. Yeah, in n choose 2, we think of the items as distinct, but we don't care about the ordering once you've chosen them. So n choose 2 is exactly it. There is another way of thinking about it. A cool way of thinking about it is you can imagine this grid. And here, let's say you have animals A, B, C, and here you have animals A, B, C. We're not going to check out anything on the diagonal. But we are going to do A and B, and we are going to do A and C. And then for B, we've already compared with A. We're not going to compare B with itself, but we are going to do C. And for C, we've already compared it with A, and we've already compared it with B. And you just kind of have these 3 different comparisons. So if there was 3 animals, 3 choose 2 would actually have given you 3. But if you took this up to more, you could imagine, OK, it's n minus 1 plus n minus 2. You're going to count how many things are in this upper right triangle. And I think it's really interesting that for n choose 2, those 2 lead to the same answer. OK, just not that important right now. But just for n choose 2, if you counted how many things are in the upper right-hand triangle, if you made that equation, you'd be able to prove that's equivalent to what this is if you were to decompose it. So n factorial divided by k factorial times n minus k factorial. OK, that was just our brief little warm-up. So really, you want to feel very comfortable with these 3 counting tasks going forward. And I know it's not easy. Counting is surprisingly difficult. But you guys seem to be doing very well considering how hard I know it is. OK, and this is a small deal, but when I was doing my PhD, the person who was sitting next to me, they were doing this research problem in computer science where they were taking samples of people's cancer cells, and then they were doing this n choose 2 comparisons of the actual DNA to come up with evolutionary trees of how cancer was evolving within people. And it led to incredible research. And now it's something that people are seeing in medical diagnosis for actually helping people's prognoses. So fun little side story. This stuff could be helpful. Well, I guess you're just counting how many calculations you do, but that's also helpful too. OK, to transition into the world of probability, I need to just introduce you to 2 terms. And these 2 terms are ones that we're going to evoke a lot. And once you feel comfortable with these terms, then we can really talk about what a probability is. The first term I'd like to introduce you to is this term of a sample space. I want to get really formal about talking about all of the outcomes of an experiment. So let's say my experiment is flipping this ridiculously large coin. Look how big that is. It's got 1 head and 1 tail. If you think about flipping this coin, there's 2 different outcomes you can get. You can get a heads or a tails. And to be really formal, that set which has all the outcomes, we call that the sample space. So if you want to say the sample space of flipping this coin, it's heads and tails. The size of that sample space is 2. Now if you had 2 coins, the sample space could be heads, 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 tails, tails, heads, tails, tails. You could define your sample space like that. What if you had a 6-sided dice? What are all the outcomes of a 6-sided dice? We have like 1, 2, 3, 4, 5, 6. All those different outcomes we think of the sample space if your experiment was rolling a dice. Just to be clear, sample spaces don't have to be, they can be infinitely large. So for example, the number of emails in a day. How many emails could you get in a day? Can't be negative. You could get 0. That's what we call a good day. 1 email is possible, and 999,999 is also possible. Any positive integer is a possible outcome of the experiment of seeing how many emails you got in a day. So the sample space, all possible outcomes, it doesn't have to be, it can be infinitely large. Similarly, it can be continuous. So your experiment could be how many YouTube, or I'm going to look in a day and count how many YouTube hours I've watched in a day. And YouTube hours could be a continuous number. Instead of being like 2, it could be 2.345. So sample spaces, the outcomes, we have this formal language. It can be infinite. It can be real numbered. Yes?
Is there any distinction between a head tail or a tail head in the flipping 2 coins?
Yeah, I think in this case, I'd like to think this is coin 1 and this is coin 2. So this is coin 1 is a head, coin 2 is a head. Coin 1 is a head, coin 2 is a tail. Very good question. OK, so sample space is just the formal name that we give to all the outcomes of an experiment. Which leads to the other term that I want to familiarize you with it, which is the event space. If you run an experiment, sometimes there's a thing you care about, an event that you care about. For example, flipping a coin, maybe the event you care about is that you have a heads. So there's just one outcome in the event space that's getting a head. Getting a tail doesn't give you a head. Maybe the thing that you care about is whether or not you got more than 1 head on your 2 coin flips. And so all 3 of these events, so head on the first coin, head on the second coin, or head on the first coin, tail on the second coin, or tail on the first coin, head on the second coin, Those three events, those three outcomes satisfy that idea of getting more than one head on 2 coin flips. So event space is some subset of the sample space that satisfies something semantic, something that we can name, like getting more than one heads on 2 coins. Here's another example. We talked about the experiment of rolling a dice, and there's 6 outcomes, but maybe 3 of them satisfy the event of getting a 3 or less on the coin, so a 1, 2, or 3. Number of emails days being less than 20. That could be the event that you're looking for, and that could be that subset of the sample space that you care about. Or, for example, you could define a wasted day to be more than 5 YouTube hours, and we've all been there at some point. And then you could say that's the subset of the sample space that I care about. Okay, so sample space, event space, some terminology. At some point in lecture, I'll use those terms, and feel free to interrupt me like, hey, can you remind me, Chris, what you meant by event space? Can you remind me what you meant by sample space? So just to put that on one slide, you have sample space, all the outcomes of the experiment, and the event space, how many of those satisfy some semantic event? Okay, yeah?
Is the subspace, the sample space, all the possible outcomes or the number of possible outcomes?
It's all the possible outcomes, yeah. And we can talk about the size of it. You could ask how many things are in here, and we'll often ask that question. But when we say the sample space, we mean all the outcomes themselves. Good question, very good question. And that's why I use the capital S. Capital S is for a set. And then I often use a lowercase number if I was just talking about a number. Yeah?
This might be like a little bit like semantically nitpicky, I don't know. I would have thought that an event is an item of the set, but it seems like an event is a subset. Is there like a name or a term or like terminology for one individual item inside the sample space?
Yeah, we call that one outcome.
An outcome. Okay.
So this is one outcome, this is one outcome, this is one outcome. And this is a set of outcomes that we give a semantic meaning to. That's a great, great question. Not semantically nitpicky at all. Okay, are you guys ready to find out what a probability really is? Okay, a probability is very simply going to be a number between 0 and 1, to which we're going to ascribe meaning towards. And I'll tell you a little bit more about that when we get into philosophy later in today's class. But let's say you talk about a probability of an event occurring. We can write it as P of E, and that says what's the probability of this event occurring. Again, this is like the events that we just talked about in the previous slide. Sometimes you'll see different notation like PR of E. It's the same thing, but just like a little bit fancier. And these people could be like, I'm so fancy right now. But that's not important. This is the notation for a probability. And even though it's a number between 0 and 1 that we ascribe meaning to, there was a moment about 150 years ago when people started to formalize what they really meant when they talked about a probability. When we talk about a probability of an event, imagine you were to repeat infinite experiments. So there'd be infinite times that you'd roll your dice. What's the ratio between number of times that those experiments led to your event divided by the number of experiments that you've run? So as you approach infinity, what does this ratio approach in the limit? So lots of experiments as it gets to infinity. The ratio of successes to number of experiments you run, that's what we really mean by a probability. To make this a little bit concrete, let's say n is the number of times I run a trial. In this case, I'm going to be throwing a dart at this board. The event is that I hit the target. When we give this primal definition of what a probability is, intuitively it's saying we're going to not run one experiment. In this case, I threw one dart and it didn't hit the board, so the probability looks like it's a 0. Don't run 2 experiments. In this case, that dart did hit the board, so you can say I've run 2 experiments, one of which has hit the board, so that ratio is 0.5. This definition is saying like as that probability, or as the number of experiments tends towards infinity, this ratio is going to tend towards what we define to be the probability. That's kind of a wild one, but it's a nice thing to have in your back pocket. Now, I will complicate this a little bit in that we talk about probabilities in lots of ways. And in fact, thinking about probabilities and where they come from and being really expansive in your ideas of it was one of the things that allowed for revolutions in computer science in the 90s and the 2000s. So here's another way of thinking about probabilities that I find is very in tune with the philosophy of CS109. Imagine you're a self-driving car. and you want to think about whether or not there's a motorcycle next to you. This is a really interesting thing because the motorcycle's either there or it's not there. However, for a self-driving car to make a smart decision under uncertainty, it recognizes not that there's uncertainty in the world, but there's uncertainty in my own understanding of the world. There's uncertainty in the car's own understanding of whether or not there's a motorcycle. So beyond just thinking about probabilities as being there's stochasticity in the world and we can think about infinite events, a modern view of probability is thinking not just that there's stochasticity in the world, but there's uncertainty in ourselves. And probability is a language for expressing that we do not know. And that makes it much more powerful. It's not stochastic. There's a motorcycle or there's not a motorcycle, but this car has to hold a belief about whether or not there's a motorcycle because the car doesn't have perfect information. So to me, a probability is much more than just there's stochasticity in the world. It is representation of what I don't know. But still a number between 0 and 1 to which we ascribe meaning. And it's still the case that from the car's perspective, let's say it had a 0.9 probability that there's a motorcycle there. The way I would interpret that 0.9 as say, you know, if this car was to live this situation infinite times, 90% of those times you would in fact have a motorcycle there. So it is a very elegant language, both for expressing just there's randomness in our world, but also we don't know things. Cool philosophy for a Friday. Okay, any questions about this? You're like, there's like, this goes even deeper. Like, is our world really stochastic in any way, shape, or form? But that requires like a glass of wine to get into. There's lots of sources of probabilities. One of the sources of probability is you can derive them mathematically. There's things in the world where we can use pencil and paper and figure out exactly what probabilities are. There are other sources of probability. Sometimes we get probabilities from data. Sometimes we can get probabilities from doing lots of experiments. But the one we're going to focus on at the beginning of class is the ones that we can just know perfectly from paper. And that will build us some intuition for when we expand our idea of sources of probability to things like data sets. One starting place for thinking about analytic probability that you can get from paper, is the axioms of probability. The axioms of probability come from this guy called Kolmogorov, who I think of as being like a 1900s Harrison Ford. No, right? Anyways, so what did Kolmogorov do before he got into the film industry? He came up with these 3 axioms of probability, and they're very meaningful for 2 separate reasons. One of his contributions was, he said, if you assume these 3 things, we can derive all of probability theory. So once you feel that these 3 things are true, all the rules that we learn in CS109 are going to then come from these 3 rules. There's this other thing which is quite subtle. Did you know there was a time when people didn't know if probability and mathematics were the same? They thought maybe probability was just this whole different thing because it was so unintuitive, and they weren't sure that all the rules of mathematics applied. So Kolmogorov also managed to tie probability theory into the deeper roots of mathematics and show how it was, in fact, an instance of all the other math that had been studied. And he did that going through counting and geometry. It's a really cool deep dive if you're curious about it. But anyways, these are the 3 rules you could start out with if you were learning probability. Though, I'm going to modify them a little bit and say, for our very first set of rules for probability, these are the 3 rules that I present to you. The first 2 axioms, and the third one is an identity which is derived from the third axiom. These are pretty easy to accept axioms. The first axiom says, every probability is a number between 0 and 1. That's great. You can't have less than 0 events happen, and you can't have more events happen than the experiments that you've run. Probabilities have to be between 0 and 1. The second one, P of S equals 1. What's S? Sample space, yeah. So what's this saying? The probability of sample space is 1? Yeah, put that in words for me.
The probability of something happening is 1.
Yeah. If you're going to say these are all the outcomes, the probability of some outcome happening is going to be 1. So it's a little tautological. It's like, I told you sample space is all the things that could happen, and the probability of something happening is 1. How about this one? What's this little c up there? Is that like e raised to the power of the speed of light? That's set notation for complement. And that's a fancy way of saying, what's the probability of e not happening? And this is saying the probability of e not happening is 1 minus the probability of e happening. And we'll prove this last one by the end of class. OK, and do you guys feel pretty comfortable about all those? I say these first two are pretty tautological. I like this third one. I feel like you can have some like deep shower thoughts. You're like, this is kind of like saying everything in the world is either a potato or not a potato. Anyways, you can think about that more deeply. Okay. Now that we know what a probability is, that number between 0 and 1, there's a special case where we can derive probabilities rather easily using counting. And this special case of analytical probability is called equally likely outcomes. Not all sample spaces are like this, but for some sample space, if you looked at any outcome, it's just as likely as another outcome. So if you think about flipping a coin, we think about the heads as being just as likely as the tails. If you think about flipping two coins, we think about the outcome of getting a head on the first coin, a head on the second coin is just as likely as a tail on the first coin and a tail on the second coin. All those outcomes are just as likely. And if you roll a 6-sided dice, we think about all the numbers as being equally likely, unless you use my pirate dice, which definitely always gives you a 6. But that's not important right now. We're talking about equally likely events. If every event is equally likely, what's the probability of any of the outcomes? Well, if there's size of S outcomes in the sample space, then if they're all equally likely, every single outcome must have probably 1 divided by the number of elements in the sample space. Let's take coins. There's 2 outcomes in the sample space. This is claiming that every outcome has a 1/2 probability. If you took that a step further, if you cared about some event E, and you want to know the probability of E, it is the case that all you have to do is count how many outcomes are there from this experiment, and how many outcomes satisfy the event I care about. And if you count those two numbers, that ratio is going to be the probability. Not always true, only true if the outcomes are equally likely. Here's an example that I want you to debug. You're going to play the lottery. What is the sample space of playing the lottery? What are the outcomes? Win or lose. Okay, so if we use this logic, we can figure out that the probability of winning should be the size of the event space divided by the size of the sample space. So the probability of win is 50%. And why not? What did I do wrong? Yeah, okay, I'm going to teach you something, and it only applies if your sample space is equally likely. Is it just as likely that you win as lose? No, definitely not. Hilariously off. Okay, great. But let me give you a situation that's quite interesting to think about where all the outcomes are equally likely. I'm going to consider rolling 2 dice. Let's roll my 2 dice. See what I get. Double sixes, a 6 and a 3. Okay, fine. How can I think about the probability of the sum of these 2 dice? Lots of games care about this, and as I mentioned to you last class, a lot of probability theory was invented by people who are horribly addicted to gambling, so they spent a lot of time thinking about dice and coins. So if I wanted to think about the probability that these 2 dice sum up to 7, when I say sum up to 7, you take the value of the first dice, add the value of the second dice, that's its sum. You could think about this by taking advantage of the fact that we think the outcome space, the sample space, has outcomes that are equally likely. So here's all the outcomes of rolling 2 dice. And here I'm going to think of this as the value on the first dice, and this is the value on the second dice. So there's a little diagram on the right to help you. So this is saying, let's say the yellow is the first dice is a 5, and the green dice has a 2. So that's what this is saying. Here's all the different outcomes. 1, 1, 1, 2. It's all the 36 different outcomes. Are they all equally likely? It's hard to prove that 2 things are equally likely. When I say prove that sample space are equally likely, it's hardly something that you could do mathematically. It's often something that you do intuitively. You'd be like, do I think it's every single one here is somehow symmetrically equally likely? And we could talk about it. It turns out in this case, they are in fact equally likely. Every outcome here is just as likely as all the others. Now, if we talked about caring not just about the probability of the whole sample space, but the probability of a particular event, the 2 dice add to 7, all we have to do is we have to count the subset of the sample space where the 2 dice sum to 7. And how many events are there? There's 6 and 1, 5 and 2, 4 and 3, 3 and 4, 2 and 5, 1 and 6. There are 6 different outcomes where the sum comes out to 7. So if you buy my argument that the sample space is equally likely, we can know the probability of 2 dice summing to 7 just by counting the event space, that's 6, divided by the size of the sample space, that's 36. Okay, now, before I jump into things, you might not believe me. You might say, Chris, I don't think that this thing you claimed is true is in fact true. So the way I'd like to convince you, because I know you're computer scientists, is I'd say, you know, okay, I claim that probably the sum of being 6 is 0.1666 repeating, but I can convince you by taking you to the code. So I wrote a little program, and this little program runs infinite times. Okay, not infinite times, but pretty close, 10 million, right? What is this program going to do? It's going to simulate that core definition of probability. 10,000 times, I'm going to run an experiment. The experiment's going to return me the dice total, and if the dice total is equal to 7, then I'm going to count that in a running sum. At the end, I'm just going to print the ratio of the number of 7s I saw divided by the number of trials that I ran. TQDM is just a cute thing that will give me a progress bar as I go, and then a couple print statements. Running an experiment, roll one dice, roll the other dice, and then add them together. And rolling a dice, just so you know I'm not cheating, is just going to give you a random number that is 1, 2, 3, 4, 5, or 6. This is also just a chance for me to show you guys some Python. If any of this seems unfamiliar to you, besides the TQDM, then maybe the Python review session would be a good thing to go to. OK, should we run this? Whoa. OK, my computer is like taking a moment to decide if it wants to run it. I've noticed if I put in that charger that it gets unhappy, but if I put in this charger, it's like, I'm gonna go so fast. New Macs, man, they're supposed to, God's like, I'm gonna have the fastest Mac in the world, and then it freezes. Okay, terminal, new terminal. A little bit of time for you guys to think about what I'm doing. So I'm gonna run this, oh. Come on. Too much suspense for everybody. Python, yay, simulate. Okay, running it. And this is what TQDM, it does this, oh, isn't that so cute? And it's like telling you how many it does. Okay, so I'm running 10 million, and after I run 10 million, the ratio that it gives you is 0.166541. And somebody out there's like, whoa, Chris was right. And somebody else is like, ha, no, you're not. You said it'd be 0.1666 repeating, and that's not. And why is it not? You guys can just all say it out loud. What, you think I'm wrong? No, I'm just checking.
The target sum is 7.
Yeah. This is the probability that 2 dice add up to 7. There's 6 outcomes that have that. Where?
The comment next to it.
Oh, ha! Lol. Well, I used to have a different demo. Yeah. Danger of comments, eh? Okay. So. Wait, but somebody has to tell me, why is this number not 0.166666 repeating? Yes?
Because we didn't go to infinity.
I went to 10 million, though. But you're exactly right. 10 million is not even close to infinity. But the closer I got to infinity, the closer this would get to the true answer. So the more I run, this will approach 0.166666. That's exactly right. Thank you very much. OK, so now that I've given you the structure, what if I asked you the probability that the 2 dice equal 2? Actually, talk about this with the person next to you, because I want to make sure that everybody's following along at this point. So if there's anything confusing, ask the person next to you. Otherwise, what's the probability that these 2 dice equal 2? OK, that's about as long as I think it was supposed to take. But maybe the question came up that you want to ask everybody. Any questions come up? We've got like 30 seconds. OK, how do we approach this problem? We have to say all the outcomes are equally likely, count the sample space, and then count the event space. Sample space is the same. There's still 36 outcomes. But what is the event space now? 1. The size of the event space is 1. 1, 1. Yeah, it's a set with a single item, which is that item. So the event space is all of the single item, and that size of the event space is 1, so that your probability is 1 divided by 36. That's a chance of getting sum of dice equal to 2. I want to talk about something which is going to be so helpful for your problem sets. It turns out I gave you 1 sample space, but there's different ways that smart people could have constructed sample spaces. It just turns out I gave us the one that set us up for success. Let me tell you about other sample spaces you could have set up for the exact same experiment. You could have said, I don't care about ordering. I just care about the set of outcomes. So you want to say, like, you know, you got a 2 and a 5, but I'm not going to say which dice gave you the 2 and which dice gave you the 5. In that case, a 2-5 is not different from a 5-2. That's a reasonable way of talking about the set of outcomes of your experiment. Here's a different way of expressing all the outcomes of your experiment. You could say, Chris, there are 11 different outcomes. The sum could be 2, the sum could be 3, the sum could be 4, the sum could be 5. Those are all the outcomes of your experiment of rolling 2 dice. There is a problem, though. Let's say you chose that last one. You say the sample space, well, actually, you can't get a sum of 1, but whatever. Bah. And bah, but like still wrong. In this case, you'd say the outcomes are 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12. And then you say your probability of your event is the size of the event space divided by the sample space. And you get like 1 divided by 11. And that's not even close to 0.116 that we got when we calculate, or what was the right answer? 0.1666 repeating. Yeah, that thing. So what's gone wrong here? It's a valid sample space. It's just not the case that the outcomes are equally likely. It's not just as likely to get a 7 as a 2. The 7 is much more likely than the 2. So this, though a valid sample space, is not one where the outcomes are equally likely, so you can't really use it to come up with probabilities. Does that make sense? That one's a little bit more obvious. This is the most subtle one, and I want to talk about it because it'll help you all avoid a mistake on the problem set, midterms, etc. If you think about the dies as indistinct, and you don't really care about which one gave you numbers, you just care about the set of outcomes, it is a different outcome space. So here's the whole sample space. There's a 1, 1, 1, 2. But in this sample space, a 2, 1 is not different from a 1, 2. And a 3, 1 is not different from a 1, 3. Does that make sense? Every outcome of the experiment is represented here. But in this case, it also turns out that the outcome space is not equally likely. And again, if we want to say the probability that the 2 dice are 7, we would get 3 divided by 20, which is closer to the right answer, but still wrong. And it's still wrong because this sample space is not equally likely. You're like, wait, why? Why is this one not equally likely, but the other one is? Somebody.
When you have 2 dice that are equal to the same value, you have doubles. Those are counted once, but when you have 1, 2 versus 2, 1, those are counted half as often as they actually appear.
Yes. So if you want to, it's easy to argue that things are not equally likely in a sample space. You just need to give 2 outcomes and show that they're different. And those 2 outcomes that you pointed out are different. The chance of getting a 1, 1 is half as likely as getting a 1, 2. There's 2 ways of getting 1, 2. The first dice could be a 1, the second dice could be a 2. Or the other way around. Whereas a 1, 1, there's just one way of getting it. So this outcome space looks equally likely, but it is not. So really tricky. You want to come up with outcome spaces that are equally likely. And the best way to do that is to think about all of your elements as being distinct. If you think about all your elements as being distinct, you will more often than not end up in equally likely outcome spaces. I have the dreaded cows and pigs problem for you. This is hard. It is going to be difficult to think through. But if you can do this, this is showing that you fully are getting the complexities and nuance of setting up equally likely outcome spaces. It doesn't sound that hard. I have 4 cows and 3 pigs in a toy box. I will pull 3 of these toys out. Every toy is equally likely on every draw. And I want to know what's the chance that I end up with 1 cow and 2 pigs. I'm going to give you guys a few options for how to approach this, but then I'm going to let you choose which one you want to approach it with. Your first step in a counting probability problem is to choose your sample space. How are you going to represent the outcomes of an experiment here? And here I think you have 2 different choices. You can think of your outcomes as ordered or unordered, and you can think of each cow as being distinct from the other cows, or you can think of every cow as being indistinct from the other cows. And it'll be a choose your own adventure, 2 of which will lead to bad times, and 2 of which will lead to good times. So here's one. You think of cow 1 as different from pig 2, and pig 2 is different from pig 3. But you think about a choice as being unordered. I wouldn't think cow 1 being the third thing would be a different outcome here. Unordered and indistinct would be 2 cows, 1 pig, and 3 cows. Those would be examples of outcomes. Ordered is I care about order. It's different from this one because I care that cow 1 came first and then pig 2 came second and pig 3 came third. And that would be different than if pig 3 came first and cow 1 and then pig 2. Even though it's the same set of distinct items, this one has order in my outcome space and this one doesn't. And then indistinct and unordered would look like this. Some of you guys are thinking, how come we have a choice? Isn't it one of these is the right way? It's a beautiful piece of creativity in this part of problem solving. You get to choose how you express your sample space. You could make this choice. All of these are valid ways of articulating the outcomes of the experiments. It's just 2 of them will lead to good answers. Questions about that before we jump in? This is a meaty problem. Think about this. Here's a meta task while you're thinking about it. You're going to choose your path, but then I want you to remember what are the tasks of this counting thing. Define your sample space, count the size of the sample space, and then count the subset of the sample space that satisfy the event you care about. Okay, and while you think about that, I will write down the thing we care about. So we have 4 cows. So 4 cows, 3 pigs, and we are going to draw 3, and we want the probability of 1 cow and 2 pigs. How can you tell I spent a little bit too many times with toy farm animals? But it turns out this is a very deep probability problem I was able to pull from that. Okay, talk about it with your friend. Think about it, explore, contemplate. Okay. Not enough time. But the way I see this is the first time you're seeing a problem of this complexity. We'll do it mostly together now that you understand how deep it is. But the real goal is, this is one of the most important problems from today, because the real goal is if you can understand the process of how to come to an answer here, it will be very helpful for you going forward. So, 4 choices. Did anyone go down this path? You can just raise your hand. A few folks. Did anyone go down this path? Not many folks. Anyone go down this path? A couple folks. Anyone go down this path? A couple folks. Okay. So one of the things that we should just do if you want to choose a path is you want to decide, are the outcomes equally likely? Now, it's easier to show that outcomes are not equally likely than it is to show that outcomes are equally likely. Let me show you one example. Let's take this outcome space. So we're going to not think of anything as distinct, and we're just going to count how many unordered elements we get. Here are 2 different outcomes in that space. 3 cows and 3 pigs. Are they equally likely? So you have 4 cows and 3 pigs in your bag. Are you just as likely to get 3 pigs as you are to get 3 cows? Yeah, the outcomes here are not equally likely. So we can't use the space. Even if we can count fine, we can't use the equally likelihood formula. And something similar here. You have cow, 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 and pig, pig, pig are 2 different outcomes in this space, and those 2 are not equally likely. It turns out between these 2 choices, they are both correct. There are 2 different paths to an answer, and they both have equally likely outcome spaces, even though here we think of that things as unordered, and here we think about them as ordered. Let's think about the first one. The sample space is all the ways you could choose 3 elements. How many things are in this sample space? So I have 7 toys, and I want to figure out all the different subsets unordered of 3 that I can choose for my 7. And I'm putting this line here because I'm going to count my sample space here, and then I'm going to count my event space over here. So how many things are in that sample space? 7 choose 3. This is not talking at all about this event. This is just the number of outcomes. So the number of outcomes of the experiment is, well, there's 7 animals, and we're choosing 3 of them. That's getting us pretty close. We have one final task to do. Count how many of these outcomes are of the nature that you have 1 cow and 2 pigs. You're like, Chris, you never taught me that counting task. But I taught you the most fundamental rules of counting. Counting by or counting by steps. And you can use those most fundamental rules of counting to come up with either a set of steps or an or that would get you to having 1 cow and 2 pigs. So can somebody think about a 2-step experiment that would get us to 1 cow and 2 pigs? Was that a... I think you know it. I think you know it.
I would have guessed.
Yeah, guessing good.
Could you pick like any 1 cow out of the 4 cows and then
That's
any
step 1.
pigs out of the...
Yeah, exactly. That's exactly right. So step 1 is it's like, I'm going to take my 4 cows, I'm going to choose 1 cow, And step 2 is I'm going to take my 3 pigs and I'm going to choose 2 of them. And it's a 2-step experiment. The number of outcomes in the first step doesn't change how many outcomes are in the second step, and that's the only rule you need in order to have a 2-step experiment. And will this 2 steps lead to a 1 cow, 2 pig combo? You bet it will. So it satisfies all the things we want. So the 2 steps. 1, you have your 4 cows, and you're going to choose 1 of them. We multiply because the step rule of counting says we can multiply, and then you had your 3 pigs, and you're going to choose 2 of them. And if you did this math, you would get the right answer for the probability of getting these 1 cows and 2 pigs. So just to put what we had on the board up here, you know, I started with ordered. Here's the unordered one. Sample space is 7 choose 3. There's 35 different outcomes. The event space, there's 4 choose 1 ways of choosing your cow, and there's 3 choose 2 ways of choosing your pigs. And there's 12 outcomes there, so your probability is 12 divided by 35. What if you'd thought about things as ordered and distinct? Well, now if you think about it, you have to construct a sample space where you care about ordering. If you want to construct this sample space, it matters what is first, second, and third. So the argument here is my sample space. There's 7 animals for the choice of the first thing in a sample. Then there's 6 animals remaining that you could choose to be the second one, and there's 5 animals remaining that you could choose to be the third. So there's 7 times 6 times 5 equals 210 outcomes if you think about things as being ordered. Now, the event space is going to be a little bit harder to calculate. There's 3 different cases where you end up, this should say pick a cow as either first, second, or third. So there's either the cow is first, second, or third. If the cow is first, you have 4 choices for the cow, then this is going to be a pig. There's 3 choices for a pig, then there's 2 choices left for another pig. In this case, the cow is second. So 3 choices for your pig, the cow is second, you have 4 choices there, and then for the remaining pig, there's only 2 pigs left to choose from. In the case where the cow is third, 3 choices for your pig, 2 choices for the remaining pig, and then 4 choices for the cow that's third. Why can't I just add those up? The OR rule of counting. I'm saying my outcomes can either come from this case or this case or this case. It must be the case that they're mutually exclusive. Why do I know they're mutually exclusive? Why is it not possible for an outcome here to be the same as an outcome here?
You're only thinking 1 pig. So
Or 1 cow, yeah.
1 cow, whatever.
I typed it.
The step in which you pick it matters.
Yeah. So here, all the cows are first. And here, all the cows are second. So there can't be any overlap. Exactly. OK, so we can add these 3 numbers up. You get 72 over 210. And very happy we can do our like dun, dun, dun. You get 12 over 35 is the exact same answer, no matter if you thought of it as ordered or distinct. So if we go back to these 2 choices, these 2 were passed to happiness, and these were 2 passed to like some version of happiness, but happiness where you're wrong on this problem. And what do we notice is the same about these? In both these cases, we thought about your animals as being distinct. Were they actually distinct when I posed the problem? No. You made them distinct. And you can do that when solving these problems. OK, question, and then question.
Can you go to the next slide?
Oh, you know I can.
Can you explain why we can multiply the 2 down over here?
Yeah.
I like know we can because of the angle of counting. I don't get why.
It's because I'm saying there's a 2-step experiment to end up with the construction of 1 cow and 2 pigs. The first step is you pick your cow. The next step is you pick your 2 pigs. And there are 2 different steps, but if you put those 2 steps together, you end up with 1 cow, 2 pigs. And because the outcome of 1 step doesn't change the number of outcomes in the second step, we can just multiply. We can use the step rule of counting. So step 1, choose your cow. Step 2, choose your 2 pigs. This is the number of outcomes in step 1. This is the number of outcomes in step 2. We multiply those numbers. Good question. Yes?
So I noticed the difference between the ordered and the unordered final numbers, 72 over 210 versus 12 over 35. There's like a multiplication factor of 3 factorial. Is that because there's like 3 spots to fill? And for example, if we were to do 4 spots, it'd be 4 factorial? Or is that just not?
Yeah, no, I think that's exactly right. So you're saying if you multiply the numerator and denominator by 6, or 3 factorial, you would get this numerator and this denominator. And I think you're exactly right. For any one unordered combination, there's 3 factorial ways that you can mix it up. So there's 3 factorial times more things in the sample space here. Fantastic, yes?
Can you explain again how we've made the decision that it has to be distinct, not indistinct?
We just did it. We're just like, I got my cows. I'm going to think of them as like their own little unique butterflies.
So how does the calculation look different if we choose indistinct instead?
So if you chose indistinct, you can do your counting, but you'll get it wrong because the outcomes are not equally likely. Because the outcomes are not equally likely, you can't solve this probability problem using counting.
Okay, so because we knew that it was not equally likely to get a cow as a pig, we know that we have to think of them each as distinct?
Yeah, if you want your outcomes to be distinct, because cows and pigs are not equally likely, in these two cases where you thought of them as indistinct, it led to outcomes that were not equally likely.
By distinct, do we mean like each of the cows is distinct, or cows are distinct from pigs?
Each of the cows are distinct from one another. So you can tell the difference between pig 2 and pig 3, and you can tell the difference between cow 1, cow 2, cow 3. Can you tell the difference between cow 1 and pig 2?
Yes.
Yeah, definitely. And here you can think of the difference between cows and pigs, but just you can't tell the difference between those two cows.
Okay.
It's like we gave them name. You're like, you're Daisy, and you're Muddy, or like whatever. And so they have their own unique names. Okay, questions?
How can we tell that, like, looking at them as distinct will have, like, equally likely outcomes, but indistinct won't?
I wish I had a clean answer for you. I've heard this question many times. It's a very good question. It's like, how can we convince ourselves that these are going to be equally likely? The truth is that distinct often leads to equally likely, but to really prove it, it would take like a deep symmetry argument. But you know, I guess that's my argument here. They're symmetric. Like there's no reason that one of these outcomes should be more likely than any other outcomes. And I would just have to argue that to you as a reasonable person.
So are we saying that it's easier to calculate the probability, or rather we should always choose the distinct option over the indistinct one?
Yeah, if you went down this path, it's not hard, it's just you'll get the wrong answer because they're not equally likely. Yeah, good question. Okay, major key here. Make your items distinct if possible to get equally likely sample space outcomes because you need equally likely sample space outcomes if you want to use counting. And I think about this as a trick, a pro tip that you should use with high probability. Okay, let's think about another problem. 5-card poker hand. We talked about on last class that there's 52 choose 5 different hands from a normal deck of cards. Of that, a subset have this special semantic meaning that we call a straight. A straight is that you have the values of the cards are in order. The suits can be anything you want, but the values must be in order. Now, all cards are already distinct, so we don't have to worry about that complexity. And we've already talked about how a hand of cards, there's 52 choose 5 of those. How could you count the subset of the 52 choose 5 hands which are a straight? So that's my question for you guys, and I do want to give you guys a second to think about it, because these are meaty problems that are worth thinking about. So how could you, now if I define this sample space for you, how could you use step rules of counting or the OR rule of counting to construct all the events that lead to 5 cards in a row, having consecutive values? Okay, I know, never enough time. Now, what I hoped you would have gotten to by that point, maybe is not the full answer, but to realize that my task here is to come up with a series of steps that if you were to follow these steps would end up constructing all of the different sets that are possible from 52 cards. Or sorry, straights that are possible for 52 cards. And to use the step rule of counting, we just need to come up with these sets that lead to that outcome. And each outcome should show up exactly once in our construction. So what are steps that could construct all of the outcomes here? Yes, an idea to get started?
I guess the first step would be picking one card out of the 52 to get it started.
Yeah, but do you need to know the suit, or do you just want to know the value?
We just need to know the value.
Okay, so you're saying pick one value to get us started. Do you want to pick the lowest value, or do you want to pick the highest value?
It doesn't matter.
Okay, well, if it doesn't matter, then let's pick the lowest value. So we'll pick the smallest number in our set, that's step 1. How many choices are there for picking the smallest value? 2, you can start straight with a 2, you can start with 3, start with 4, 5, 6, 7, 8, 9, 10, or jack, right? Jack, queen, king, ace. No, you can only get to 10. Yeah, no. We don't count that as a straight, playing poker hands. So 2, 3, 4, 5, 6, 7, 8, 9, 10. There's 9 choices for the value of the first card. It's like I'm teaching counting at Stanford, and I can't even go from 9 to 10. Are we sure? 2? No, you can't start with an, you can't start with an ace. Okay, you're right. So it is 10, right? Yeah, ace, 2, 3, 4, 5 counts as a straight. We're not learning poker here, we're learning counting. Okay, at this point, do you have a full hand? No, you've only defined one value. Once you know that, let's say without loss of generality, that you've chosen your lowest value to be a 2. We now need to choose the value of this card. But wait, do we? We already know it's going to be a 3. And how about the value of this card? 4, 5, 6. So once you've chosen a number, are we done? Someone thinks we're not.
Can't we also get a 4 or a 5 after the first card and then get a 3 later?
That's a very good point. We don't care about ordering here. So we don't think about any card as being first or last. So like a 2 followed by a 3 is going to be the same as a 3 followed by a 2. So in this 52 choose 5, we're in this world where we don't think about ordering. It's not the 52 times 51 times 50 that would have meant that they're ordered cards. Very, very cool. So your event space should match your sample space. So that means we're going to construct things that are unordered. Such a good question. Okay, so they're unordered. Once you've chosen one card, we know the value of all the other cards. Are we done? Is this just 10 divided by 50 choose 5? No, because I've just constructed values. I haven't chosen suits. I haven't told you that this one's a heart and this one's a diamond and this one's a... And I need to choose suits because in this sample space, all my cards have suits. So in this event space, which is supposed to be a subset, all my cards also have to have suits. So let's choose it. How can I choose a suit for this card? The 2. Yeah, there's 4 choose 1. Fun fact, 4 choose 1 is 4. So there's 4 choices for the suit of card 1. How about for the next card? But isn't there just, are there 3 suits left or are there 4 suits left? 4. Yeah, because it doesn't matter what suit the 2 is. The 3 can be any suit. Okay, there's 4 choices for the next, and then 4 choices for the third card, 4 choices for the suit of the fourth card, and 4 choices for suit of the last card. I sometimes, when I do this, like to write arrows, be like, choose starting number, choose the suit of the first card, second card, third card, fourth card, fifth card. But this is 10 times 4 times 4 times 4 times 4 times 4. Will that construct us a set that is a straight? Oh, am I missing something?
You have an extra 4.
I have an extra 4. No, I have the right, finally. Well, because there's 1 4 for every card and there's 5 cards. You have to choose the suit of every single card.
I still don't fully understand why it's a 10 at the beginning.
Okay, so your choice was, I want to choose the lowest number in the straight. So maybe in this case, the lowest number in the straight is a 6. In this case, the lowest number is a 2. And so let's do this. Your lowest number can be an ace. It can be a 2, it can be 3, it can be 4, it can be 5, it can be 6, 7, 8, 9, and it can be a 10. So there's 10 choices for your lowest number. And then once you know your lowest number, the values of the next cards are already set for you. If you tell me your lowest number is 6, I know the other ones are 7, 8, 9, 10, because I know it's a straight. Yes?
So here we were like finding how many straights we can get as opposed to the probability of getting a straight in the next 5 rounds.
But this, we counted how many straights you could get, but you should divide that by 50 choose 5, then you get a probability. So this ratio is the probability because of equally likely outcome spaces. Okay. One question in the back.
One question. Is this taking into account the fact that you remove a card from the deck every time you draw one?
It is. Because in this sample space, when you do 50 choose 5, it doesn't allow you to choose the same card twice. So when you do choosing, you're not getting the same thing multiple times. It's not with replacement. Very good. Okay. Fantastic. Something to think about. Here it is in the slides, but we've already done it on the board. Couple pro tips if you find this hard. If you find it hard to come up with an answer, just write one example of one outcome. And then try and make sure that you convince yourself that every outcome is equally likely. And then you construct, after you've counted the sample space, then you count your event space. And the probability of your event, if they're equally likely, is the ratio of those two numbers. OK. I'm going to leave straight flush up here. Oh, actually, maybe this is interesting. A straight flush is when all the cards also have the same suit. So maybe they're all hearts, or they're all clubs, or they're all diamonds, or they're all spades. So some people don't consider it to be a straight if it's also a straight flush. So what's the probability of being a straight but not a straight flush? I just want to show you, in this case, again, the sample space is the same. We're just going to try and count how many hands are straights but not straight flushes. And this is just an example of, OK, if you count the number of straights, and you don't want to include the number of straight flushes, you can just subtract out how many straight flushes there are. So the event space will be all the straights minus the straights, which also happen to be straight flushes. Choose your value, and then choose one suit. And you don't have to choose any other suits if you're making a straight flush, because there's only one choice. This number is much smaller than this number. So if this was your event space, it'd be a much smaller probability than this if this is your event space. Straight flushes are much less likely than straights. OK. So key tip. If you're given a problem that looks like an equally likelihood probability problem, you want to start by defining your sample space, what's the outcomes, write a couple of those out, and then define what the event space is, and then get to counting. And counting is often going to use things like the step rule of counting or the OR rule of counting. OK, my final example. N chips are manufactured, and we're going to assume that exactly one is defective. You're going to test some set. I'm going to not test every single one of my N chips. Instead, I'm going to test K of them, and then I'm going to see what's the probability that the single defective chip was in my K chosen ones. Because if the single defective chip was in my K chosen ones, then I catch it. And if it's not in my K chosen ones to test, then I don't catch it, which is sad times. So the question is, could you figure out this probability? I'm going to let you guys think about it, but I'm also going to combine it with your 2-minute pedagogical pause. So I'll give you some time to think about it, but I'm also going to give you a little bit more time so you can go to the bathroom as you like, whatever you need. Sorry. Let me see. Yeah, let's see if that's going to hit. OK. OK. Yeah. Talk about it afterwards.
Afterwards?
OK, yeah. OK. I know I've thrown 3 pretty hard questions at you, but I have this pedagogical idea that if I give you lots of examples, when you get to your problem sets, things will be much easier. So if I give you a breadth of examples, even though they're hard, if you're willing to work through them, it'll leave you in a good place. So this is another instance of a problem. We have N chips. 1 is defective. We're going to choose K randomly to test. That's out of the N, so K must be smaller than N. And what's the probability that you, in your test set, you happen to get the defective group? I'm going to use this as a chance to give you guys some more pro tips. Let's assume this is quite hard. One thing you can do that's adding complexity, or one thing that's adding complexity, is these variables. N and K are making things a little bit harder than they need to be. And if you find a problem like this hard, give concrete numbers. So let's say N is 7. So you have 7 chips. And I'm just making this up so that I'm making it concrete so that when you're thinking it through, you could also think about it with concrete numbers. Let's set K to be 3. And obviously, when you give your answer, you're going to have to give the general one where N could be any large number and K is any number that's smaller than N. But by thinking about 7, 3, doesn't it become a little bit easier? OK, so let's think about this. what are the steps to solving a problem like this? We want a probability, but if we can find a way to construct a sample space that's equally likely, we can solve this problem using counting. So your first step would be, can I figure out how I can do a sample space where things are equally likely? So, you know, I could think there's n chips, and I could choose maybe 3 of them in order. And I could say there's 7 times 6 times 5 different ways of getting 3 chips in order, thinking about them as distinct. Or I could say I want to choose a subset. I'm thinking of the sample space. So I'd say there's 7 chips, and we're going to choose 3 of them. That's my sample space, all the outcomes of my experiment. I don't think you could use bucketing for this one. So which one do you guys like? Which sample space? And maybe we should draw an example of them. So in the first example, sample space, we're thinking of them as ordered. So like you choose chip 7 first. Or I'll say C7 for chip 7. And then you choose C1 next for the second chip. And then you choose C2. And we think about this as being ordered. If you think about it as just the choose operation, your sample space would be like C7, C1, C2. It's the same grid of options you had when we had the pigs and cows. You think of your chips as distinct or not distinct, and you can think about your outcomes as being ordered or not ordered. But we learned from that experiment that it's better to think about them as distinct. And in that case, it turned out it didn't matter if we thought about them as ordered or not ordered. Yes?
In this case, we don't know what probability of a zero each chip is. So they could all be great, or they could all be horrible. That has been described them.
Yeah, there is one thing. I'm going to tell you that exactly one chip is defective. Oh, you're saying that you're saying that like one of these could be the defective chip. Like I should have a special symbol for the defective one.
Sure.
Okay, so it could be like chip 7, chip 1, and the defective one. Yeah, good. So if n is 7, there's 6 healthy chips and 1 defective one. Very good. Helpful clarification. Okay, what's our sample space? What are all the outcomes of the experiment of choosing 3 to test? Okay, 7 choose 3. I heard a lot of people say 7 choose 3. That's the size of the outcome space. If you think about any one of those outcomes, it's like it's got 3 chips in a set. So there's 7 possible chips you could have chosen from. You choose 3. And in this case, if you wanted to write it more generally, you would write n choose. You wouldn't write 7 and 3. You would write n and k. There's n chips, and you're going to choose k of them. Those are all the outcomes, but it doesn't describe the event space. And the event space is the outcomes where you happen to get the defective chip. So every outcome in the event space better have that defective chip in it. So can we come up with a set of steps that will come up with an outcome that does have the defective chip in it? Yeah.
Would it be 2 choose 7 choose 2 and multiplied by 7 choose 1?
So, okay, but what are those 2 steps?
So 7 choose 2 would basically be choosing 2 non-defective ones.
Okay, so you have 7 chips, and you want to choose 2 that are not defective. But it's not the case that all 7 are non-defective. So your first step is to choose your 2 non-defective ones, right?
So it would be 6 choose?
Yeah, and particularly it's n minus 1, because there's n minus 1 chips that are not defective, and you want to choose k minus 1 of those. 6 choose 2. So there's 6 non-defective chips, and you're going to choose 2 of them. There's 3 chips in this set. That last chip is going to be defective. So we're going to choose 1 defective chip out of how many defective chips? Yeah, and guess what 1 choose 1 is? 1. And guess what 1 multiplied by anything is? 1. Woohoo, that's just 1. Bye-bye. Okay, you guys got it. That's absolutely the right answer. Okay, so the sample space, there's n choose k different ways you could choose the chips to test. Of those, the ones where you caught the chip you cared about, you could use the step rule of counting to construct all of those outcomes. First choose your defective chip, and then choose your non-defective ones. In our case, we did this in the other order. Does it matter? No, it doesn't matter if you choose your defectives and then your defective. You're in your non-defectives afterwards. Okay. Now, for those of you guys who are interested in not just having this formula, but trying to make it a little more simple, you could take this formula and apply it to the actual combinations formula, and this is what that would give you. And the same thing on the bottom. You can apply the actual combinations formula. And if you're willing to sit with this for a second, if you do all your canceling, it gives you k divided by n. What? Huh. So, how could you, is there a way you could have just gotten to this answer a little bit faster? One way of thinking about it is to think, you've got n chips here. So I'm going to draw my n chips. This is not that important, by the way. If you see the problem one way, that's sufficient. But this is just kind of fun. Here's my n chips, of which one is defective. It's kind of like you're going to have k shots at these. Oh, wait. Oh, sorry. Let me try that again. I got my formulation wrong. Here's my n chips. And of this, I'm going to choose the k that are the ones that you test. Now imagine we're going to place the defective chip over here. So what are all the different places where you could put the defective chip? Like if you count the different locations where I put the defective chip. How many different places could I'm going to first put all my chips there. Then I'm going to circle out all the ones that I'm testing. And now I'm going to imagine I'm going to throw the defective chip somewhere on one of these. Weird, weird, weird construction. I'm just being playful here. The other answer is the more straightforward one. Imagine the defective chip was a dart and I was throwing it at all the chips. It could land on any of these n places, right? And they're all equally likely. So you can imagine there's n outcomes of this super weird experiment. In this sample space, there's n outcomes. Of which, if the defective chip hits here, did I catch it? No, because it wasn't in this tested set. If it lands here, did I catch it? How many of these outcomes will I catch? There's k of them. So k divided by n. There's n places I can throw my defective chip, of which k will lead to me catching it. Such a weird, weird way of setting up a sample space, but hey, it works, and it gets the right answer. Okay.
That suggests that you should be mindful of how you take your sample, or take a larger sample.
Yeah, because it does suggest that you can be mindful, because if you were really creative and thoughtful, you could have saved yourself a lot of math. But at the end of the day, these two things do give, if you did the math, you get the same thing in both ways. But you're right, the sample space here is really large. If you had to save this whole thing in memory, that would be a huge problem. If you had to save all these outcomes in memory, not a problem at all. Okay. This is a little bit less important, so I want to spend a little bit less time on it. Actually, I'm going to leave it there just for something to review if you're curious. In fact, though, actually, we are out of time, so this is probably the place where I should pause and let us continue. But I did promise one thing that I want to make sure I am good on. So if you have a moment, I told you by the end of today's class I would do something that has never been done in the history of the world. You guys ready for it? See this deck of cards? You ready? I'm shuffling it. I'm shuffling it once, not once. I'm shuffling it twice. Wait for it a third time. And then, let's just do it really fast. 4, 5, 6. The reason I shuffle it 6 times is there's a professor at Stanford who's proved that using a cool thing of chaos theory, once you shuffle a deck of cards with 52 cards 6 times, every ordering is equally likely. Ladies and gentlemen, this ordering of cards has never been seen in the history of the world. No one has ever seen this exact ordering. Never, ever, and I am so certain of it. You could get this by thinking about sample spaces and event spaces, but basically, how many orderings are there of cards? There's 52 factorial. 52 factorial is so bloody large that even if you think about a sample space of people shuffling over the history of the world, no one has ever seen this set of cards before. Ladies and gentlemen, have a fantastic weekend. We'll see you guys back on Monday.